turns out that the neutron, being heavier than the proton by about 1.5 MeV, can decay into a proton and an electron and a neutrino in a process known as beta decay, beta because it produces the electron. And we write that interaction like this. The neutron goes to a proton and an electron, and as it turns out, an anti-electron neutrino. Originally, when this kind of decay was discovered, the neutrino wasn't there, but the electron had a range of energies, and you would expect from two-body decay kinematics, if the neutron just went to a proton and an electron, that they would have fixed energies, with the electron coming off with a fixed energy. But the electron had a range of energies, and so Pauli introduced the neutrino, the little neutral one, to account for the kinematics of that. The neutrino is almost massless. It's much, much lighter than the electron, and therefore you couldn't tell its energy for a long time. Turns out that there's a similar process. If we have an electron available, we can combine a proton and an electron with some extra kinetic energy in that interaction to create a neutron, and in that case a not anti-neutrino, just a regular electron neutrino going out. This is called inverse beta decay, and but it won't happen unless we add energy. If we shoot the electrons into the protons, then we can create this interaction. However, in the nucleus, we can sometimes take an electron from the atom, combine it with a proton to create a neutron, using available energy to do that. And so, using these two interactions, we can change a neutron into a proton or proton into a neutron, and that allows nuclei to change along isobars. Notice that if you change a proton into a neutron, you're not changing the atomic weight by very much. You just have the small weight of the electron. So we can use this to figure out, based on the semi-empirical mass formula, what the most stable isobar of any particular element is. So if we rearrange terms in the semi-empirical mass formula, we can say that the mass for some z and a is alpha times a minus beta times z plus gamma times z squared plus delta times 1 over the square root of a. And the alpha, beta, gamma, and delta terms, I'll tell you now what they are in a second. But note that this, if we ignore the delta term, we have, and a is fixed. So if a is fixed, this is a constant. Then we have a quadratic in z, which will have an upward curvature. And then the delta term is going to be the pairing term, which may or may not affect it, and we'll see what that does in a second. But so it turns out, so if we fix A, then there will be one Z at which the mass is, from the semi-empirical mass formula, is the least, and that one is the one with the most binding, and that will allow us to predict some things about beta decays and inverse beta decays in the nuclei. So just to make sure, so the alpha parameter here is the mass, we take the mass of the neutron minus the volume term, A1, plus the surface term, A2, over A to the 1/3, cube root of A, plus the asymmetry term, A4, over 4. The beta parameter in the quadratic is the asymmetry term, A4, plus the mass of the neutron minus the mass of the proton minus the mass of the electron. The gamma term is the asymmetry term A4 over A plus the Coulomb term A3 over A to the 1/3. And finally, the delta parameter is just the pairing parameter, A5. And so if we recombine this, we get a quadratic. If we fix A and have a set of isobars, there'll be a minimum mass, maximum binding energy at the Z min of beta over 2 gamma, just solving the quadratic equation. So then let's look at a couple examples. First for odd A, where the delta parameter is 0. And in particular, let's pick this case of an A of 111. And I've used a table of nuclear masses for this with the binding energy as shown here. So minus from the, just the total masses, the mass deficit from that in MeV. So we're down about a GeV at the minimum, but the range here is a few tens of MeV. By the way, that's this line across the nuclide chart. And so some of the examples here then are going to be, well, Z min in this case with, so A is 111. We plug in the parameters, we find Z min is about 48, which is cadmium. And so we can have, if we go to elements lower in Z, so cadmium would be here. If we go to the next one over, it turns out to be silver, 47. So the reaction that we find is that silver, 47, goes to cadmium, 48, plus an electron, plus an antineutrino. And so that is this interaction going from this one to that one. It's not a very big change in energy, but it still goes to a lower energy, including the mass of the electron. And it turns out this has a lifetime of 7.5 days. If we go next over, we can also go from the 46 to the 47, and so we get an interaction that is 111 palladium 46 can go to silver 47 plus an electron plus a neutrino, antineutrino. And this has a half-life of 23 minutes. So it's a bigger change in energy, and it has a shorter half-life. That tends to be the case, though there can be weird things with spins that make it not a perfectly applicable law. We can keep going in this fashion. Rhenium 45, 111, goes to palladium 46 plus an electron plus a neutrino. This has a lifetime of about 11 seconds. On the other side, you can get the inverse beta decays. So you can have indium 111 49 goes to cadmium 48. But in this case, it just gives a regular neutrino, and I forgot, it takes an electron here. So if you have an atom of indium 49 with its electrons around, it can grab one of those electrons orbiting and do the inverse beta decay to cadmium and release a neutrino in that. And this has a lifetime of 2.8 days. It's important to note, however, that the electron has to be there. If you completely ionize indium 49, and it will not undergo this inverse beta decay because there's no electron available. Then finally, going a little further, tin 50 plus an electron goes to indium 49 plus an electron neutrino, and that takes 35 minutes. And so in all cases along this, we move towards the bottom, and notice, sorry, I think I pointed out the last one last time. This is the line we're going along, the blue line there. Notice there's only one stable nuclei there, and that would be the cadmium 111. So let's then go to the interesting case where A is an even number. And we'll use 102 for this example. And so A102, it's this line along the Segre chart. The interesting thing here is the even number of neutrons and even number of protons gives a stronger binding than the odd number of protons and the odd number of neutrons. So that we get two parabolas, the red parabola here for the even case, and the green parabola for the odd case. And so in this case, the Z min is 44, is around 44. And so we expect that ruthenium 102 is stable, and it is. And so the interesting thing, though, is that and so if we go to the odd cases of, having Z equals 45 or Z equals 43, and also an odd number of neutrons, both of those will decay by beta decay in the 43 to 44 case, or inverse beta decay from 45 to 44 into ruthenium 44. But we have the interesting case, because of the split, that the 46, actually it's not the 46, it's the 42, or no, sorry, it is the 46, is stable because its energy, its mass is less than the 45 case, so that both palladium 46 and ruthenium 44, both with 102 nucleons, they're both stable. And the reason they're stable is because the palladium 46 would have to go to a higher energy state. So it's kind of in this local minimum of mass energy. And so the inverse beta decay is not energetically allowed for it. It is interesting, you can sometimes imagine that you would have a double inverse beta decay, in which you'd have something like 102 palladium 46 plus 2 electrons goes to ruthenium 44 plus 2 electron neutrinos. And this would be called double beta decay, or double inverse beta decay. In this particular case with palladium, that has not been observed, but there have been a few cases of double beta decay observed For instance, 82 selenium 34 goes to 82 krypton 36 plus 2 electrons plus 2 electron antineutrinos, but this has a lifetime of 10 to the 20 years, which is a really long time. Basically, you have to have at least 10 to the 20 atoms of selenium-82 and look at them for a year to be able to see this kind of decay. And so because this involves two weak interactions together, it's a second-order weak interaction, and that's why the half-life is so small. So in essence, then, if you have an even isobar state, a set of isobars with even numbers of with an even number of neutrons and protons, it is possible and quite common to have two stable nuclei amongst that set of isobars. So odd ones, there's always only one. Even there are often two stable nuclei. It's also true that there are never two stable nuclei amongst a set of isobars next to each other. They're always, if there are two, they're always separated by two. You have to change two protons into two neutrons, or two neutrons into two protons in order to have the two stable states. Okay, finally today let's talk about alpha decay. It's the other kind of decay that can happen, and it happens because the alpha particle, helium alpha, that's the same as helium 4-2, is very, very tightly bound, more tightly bound than predicted by the semi-empirical mass formula, more tightly bound than anything. And so it's common to have the process where you have some some nucleus, I'm going to just call it Z, which has some, let me not call it Z, let's call it Y. Y is an actual element, but I mean it to be a general name for an element here. Some arbitrary element Y with some Z and some A can go to some other element, call it Y prime, with A minus 4 and Z minus 2, plus the alpha particle, 4 and 2. So the Z's add up, the A's add up. This is actually a two-body decay, so the alpha particle coming out of this decay has a fixed energy. It will always have the same kinetic energy. The total energy released in this is split between the nucleus left behind and the alpha particle, but since this is only common for A greater than 100, then the alpha particle usually has most of that kinetic energy because it's the recoil nucleus is much, much heavier and moves much more slowly. Now, it is interesting how to consider this. If you remember from our Fermi gas discussion, we had a model that looked something like this, and we had paired neutrons and paired protons in each one of the energy levels up to the top level, and they go down. And if we think of the top level here, if we take this set and we say, okay, there's two protons and there's two neutrons, and their spins are all paired, and we can furthermore pair them to get a spin zero helium nuclei, and the helium nuclei, or the alpha particle, does have spin zero. We can recombine and say, okay, rather than having a gas of fermions, neutrons and protons, if I combine them in sets, I could have a gas of bosons, these spin zero alpha particles. That works somewhat for carbon 12 and oxygen 16. You can Think of it that way. It doesn't work so well for other states, but we can consider there to be one highest energy alpha in a well of the rest of the particles, in which case, in that recombination, it might have an energy greater than 0. So if we imagine that the last alpha is in a well like this, and it has an energy level up here. So it is bound, it's still inside. All right, so here's the energy of the alpha, the highest energy alpha that you can put there. It has an energy that is above 0, and it can tunnel through the barrier, and in which case, once it comes out, it has that energy above the above 0, and so the kinetic energy it will have in the decay will be just this. You have to do the kinematics. It's not quite that. Some of that energy goes into the recoil nucleus, but most of it goes into the alpha. And it turns out that you can relate that to the thickness of the barrier. And we know, so remember back to modern physics class, if you have a particle going through a barrier, it cannot exist in this area. The alpha particle cannot exist here, but it can tunnel through that barrier. Okay, so that's a simple qualitative statement. The quantitative statement is that the bigger the barrier is, the longer it, or the less likely it is to tunnel through, or the longer the half-life of this particle for alpha decay. So there is then a relation between the energy of an alpha particle and 1 over the lifetime of the alpha decay particle. So these aren't exactly proportional, but they are related and monotonically connected at some power. That as the lifetime goes down, meaning that you have less to tunnel through because it happens faster, then the kinetic energy is higher. And if the kinetic energy is lower, because you're here, you have a lot more to tunnel through, and then you come out with much less kinetic energy. So there's a relation between the kinetic energy of alpha particles in alpha decay and the lifetime of the nucleus that produces them.